Nice invitation to come here. My name is Bastien Lapierre. I'm a postdoc since last October in Princeton University, working with Shinsei Ryu. And before that, I was a PhD student at the University of Zurich, working with Titus Neupert. So today I'm going to talk about some recent works that we posted on the archive about 2 weeks ago on some kind of universal chaotic features of a large class of driven critical systems, periodically driven critical systems. So yeah, this work was done in collaboration with Tokiro Numasawa from Tokyo, Titus Neupert from Zurich, and Shinsei Ryu from Princeton. And it's been posted on this archive link. But part of my talk, and actually a large part of my talk, will also be based on some previous papers that I wrote in collaboration with Ramasubramanian and Chitra, Kenicho, Per Musavi, Clement Ober, and Apuf Theory that are available at this in this PR research and this PRB. So as the title of the talk suggests, I'm going to talk about quantum scrambling. So very loosely speaking, quantum scrambling is the fact that local information may be lost and spread in the interaction in a many-body system. There's been a lot of refinement over the last decade to understand what could be good measures of this scrambling of information. So one of the most prominent, perhaps, notions was the so-called out-of-time correlators, or OTOCs for short, which are this basically correlation functions, this commutator square of two operators V and W inserted at different times. So this kind of correlator has a very peculiar time ordering of its operator that somehow captures this scrambling in the system. So it is believed that in a chaotic system, the OTOC should grow exponentially exponentially fast at early times. There's been some measurements of OTOCs in NMR experiments in trapped ion and superconducting circuits, though most of the time the experiments were limited to rather few body systems because in part of this very peculiar ordering of the operators that needs, that needs in an experiment to design backward time evolution, which may be tricky sometimes. So here there's an illustration from a PRX paper from 2017 where they looked at, they experimentally extracted OTOCs for in an NMR experiment in a 4-body system. So there's been a lot of intensive research both from, let's say, condensed matter community, but also high energy physics community and quantum information community in these OTOCs, because it is believed that this early time exponential growth is characterized by some Lyapunov exponent, the exponential rate, and it's believed that this rate is somehow bounded by the temperature of the system. So this lambda L equals 2 pi kBT over h bar is sort of the upper bound of the Lyapunov exponent. And it's believed that black holes kind of saturate this bound on quantum chaos. So a very important step that was made to kind of substantiate these claims from Maldacena, Stanford, and so on, was the SYK model. The SYK model is known to be to have a holographic dual in the large N limit, and it's been shown that it does saturate the bond on out-of-time correlators. So that was kind of one of the models that kickstarted the very growing interest for all these notions. So in my talk, I'm going to talk about non-equilibrium phases and Floquet engineered systems, so Floquet driven systems. So I guess in this crowd, I may not really have to really introduce what these are, but okay, these are systems that are subjected to a time-dependent Hamiltonian that is periodic in time. And with this sort of time-dependent Hamiltonians, one can engineer all sorts of interesting phases of matter. So for instance, Floquet topological insulators that can be obtained by radiating light on the graphene that opens a topological gap. It's been realized on surface of 3D TIs. There's also, of course, discrete time crystals that have been realized in some quantum processors. But in general, there's some limitations in trying to design these driven phases that comes from the fact that as you drive the system with this periodic Hamiltonian, you may heat up and essentially thermalize and just go to a featureless infinite temperature state. In fact, there's been experiment in some weakly interacting Bose-Einstein condensate subjected to a periodic optical lattice that where this Floquet drive was leading to parametric instabilities in the Bose-Einstein condensate. And as you see on these figures, as the system was driven, essentially, the Bose-Einstein condensate is kind of destroyed. So yeah, the general paradigm is that for generic Hamiltonian, generic many-body systems, as you drive the system, you will heat up to an infinite temperature state and follow a volume law of entanglement. On the other hand, there are very notable counterexamples to this. There's many-body localization that can escape that heating fate. There's also quantum many-body scars, where part of the spectrum will actually not follow volume law of entanglement. In this talk, we'll be interested in integrable systems, which of course are a special case, right? Because they have this extensive amount of local conserved quantities, and this system may or may not heat up depending on the initial states, the integrals of motion, the drive, and so on and so forth. And the nice thing, of course, is that there's a very large toolbox to study these integrable systems, both analytically and numerically. And the type of system that we will concentrate in these talks are critical systems in one dimension, whose low energy is usually well described by a conformal field theory. Essentially, their continuum limit has conformal invariant that comes from the scale invariance that you have at criticality. So in a nutshell, this talk is going to be essentially considering some very large class of quantum critical models whose low energy description is a conformal field theory, and essentially drive these quantum critical systems with a time-dependent Hamiltonian that will be time periodic. The way we'll design this Floquet drive is in such a way that this conformal invariance somehow remains, and one can still study the system more or less exactly. And what we find is that there's some interesting spatially structured heating phase where we have emergent black hole excitations that emerge in the system in some parts of the system. So these excitations will absorb all the energy and all the quantum entanglement in the system. And we will be trying to understand whether these kind of emergent black hole-like excitations can have anything to do with scrambling, right? Because before I was telling you that usually, like, real black holes are known to scramble, to be the fastest scramblers of quantum information. So can we somehow see something like this in a system where one has some sort of analog black hole excitations? So yeah, this is basically going to be the roadmap of this talk. So let me first introduce the types of system that we'll be interested in. So as I mentioned, we'll be looking at critical lattice models in one dimension. So you could think of the XXE model, you could think of the transfer phasing model, and so on and so forth. The whole point is that the low energy physics of these systems is conformally invariant. This you can see, for instance, if you do DMRG on these spin chains, you'd see that, for instance, the scaling of the entanglement entropy goes as the log of the subsystem size, and the prefactor is, of course, the famous central charge that kind of classifies these different CFTs. So, for instance, C, the central charge, is 1/2 for the Ising model, the transfer field Ising model. C equals 1 for the free boson, the XXE model, and so on and so forth. So what we'll do is that we'll try to deform these critical models in a way that somehow the low energy is still some sort of conformally invariant in some, maybe is still somehow conformally invariant. So the way to do it is the following. We'll spatially modulate the energy density in space. So now in our Hamiltonian, we'll multiply the Hamiltonian density Hi by some function Fi that varies very smoothly compared to, let's say, slowly compared to the length scale of the lattice spacing. The point is that by doing this sort of, very slow deformation of the Hamiltonian, the low energy description of this sort of models will still be a conformal field theory, but we'll call it an inhomogeneous conformal field theory, which will still be conformally invariant, importantly. So we'll still be able to use the main tools that make CFT so, appealing and tractable. So yeah, despite the lack of translation invariance of that kind of system, we'll see that we can actually say a lot on the evolution of a lot of different quantities as we, for instance, quench or drive with this sort of deformed Hamiltonians. So yeah, let's try to be a bit more concrete. So we'll consider a deformation, a spatial deformation that consists of a single harmonic. So very concretely, the function f of x would be given by a single Fourier mode. Let's say here, for instance, is the q harmonic. So q here is an integer. So q equals 1 will be the first Fourier mode, q equals 2 will be the second Fourier mode, and so on and so forth. And then this deformation is just characterized by three numbers, alpha, beta, and gamma. So it's really just, a single harmonic here. It's perhaps the simplest types of spatial deformation that is smooth that we could imagine. And we can try to write a continuum Hamiltonian for this system. So the continuum Hamiltonian will take this form. It's a inhomogeneous Hamiltonian. So it is basically the integral over space of T00 of x, which is the energy momentum tensor, times f of x, which is our spatial deformation of the energy density. Here, in a bit more of a technical note, which is not very, for those who don't know what Virasoro generators is not so important. But what I would like to mention is that because f of x contains a single Fourier mode, we can decompose this Hamiltonian in terms of the sum of only three Virasoro modes. L0, which is the usual Hamiltonian in CFT, and LQ and L minus Q. So basically, because we select the Q Fourier mode, that will select two additional Virasoro modes in the Hamiltonian. Instead of only having L0, now we have L0, LQ, and L minus Q. And this note is rather important because it turns out that L0, LQ, and L minus Q form a closed algebra. It's called the SL2R algebra. Maybe you've seen it in a lot of different contexts in quantum mechanics. And this sort of very simple algebra that has three generators will help us a lot to understand what's the time evolution of fields under this Hamiltonian. So we can write the time evolution of fields in Heisenberg picture. That's the definition, right? We want to evolve for a time t with our deformed Hamiltonian H, a field phi of x. And essentially what we can do is that we can basically make a change of coordinates. So we can basically go now to some sort of new coordinates where our Hamiltonian is uniform. Then we do time evolution with the usual uniform Hamiltonian in those coordinates. And then we go back to our original lab coordinates. So all that is encoded in that equation here. So Z tilde is a coordinate transformation on the complex plane that basically is time dependent. So it's called a Möbius transformation. It is of the form AZ plus B over CZ plus D. And the coefficient A, B, C, and D are explicitly time dependent. So in a sense, you reduce the time evolution of the field to essentially finding the field in new coordinates, which are time dependent. This equation is saying nothing more than that. So yeah, that's the basic idea. We can encode time evolution with this inhomogeneous Hamiltonian by a change of coordinates, by a conformal transformation. And in this case, this conformal transformation is a Möbius transformation. And in particular, it has very important consequences because eventually we're interested in always, looking at correlation functions. This is what gives us, for instance, entanglement entropy or energy evolution and so on and so forth. So in order to evaluate this non-equilibrium correlation...
Sorry to stop you. Sorry. So yeah. This particular transformation is done because you are working with a CFT, right?
Exactly. Here, this is all at the level of a continuum Hamiltonian.
That's why the time evolution can be mapped to a coordinate transformation. Yeah.
Exactly.
Oh,
exactly.
Cool. Thanks. Yeah.
Yeah, and we know how primary fields change under coordinate transformation. That's essentially that equation here in CFT. It is
That's right. Yeah.
We know how that's basically the definition of a primary field. Yeah.
Right. Thank you.
So the very good thing about this is that then on the left-hand side, we have these non-equilibrium correlation functions that in principle are hard to compute, but we can just relate them on the left-hand side to equilibrium correlation functions in some new time-dependent coordinate Z tilde. So that is, okay, without going too much into details, that will be the basic philosophy that we'll do here. We'll always encode time evolution in this change of coordinates, and thus non-equilibrium correlation function will map to equilibrium correlation functions in time-dependent coordinates. So yeah, that is the basic idea that we want to follow here. And now we can try to be a bit more concrete and design some Floquet drive. So the simplest way we can design a Floquet drive is to do what's called a bang-bang Floquet drive. So we have two static Hamiltonians, let's say H1 and H0. We evolve H1 for time t1 and H0 for time t0, and that forms our one-cycle evolution. Then we basically choose H0 to be the uniform critical theory, so the one, the usual one. And H1 will be a spatially deformed version of it that involves a single Fourier mode, as I just described before. And now we'll try to alternate between H0 and H1 and find what is the stroboscopic evolution of fields. So you can write a one-cycle Floquet unitary. By definition, it's just this, right? You evolve for H0 for time t0 and H1 for time t1. And then you're interested in the stroboscopic evolution of the fields. So you were interested to find in Heisenberg picture the cycle evolution with the Floquet unitary of the field. But again, the evolution with H0 can be encoded in a conformal transformation. Same for H1. These are Möbius transformations. So now you can start to basically compose this transformation with each other, and that will give you the stroboscopic evolution of the problem. You can write down a one-cycle transformation, the transformation that encodes the time evolution for one cycle. It's a Möbius transformation. And then you can compose it with itself n times, and that would give you the evolution after n cycles. And that comes about because Möbius transformation have the very nice properties that as you compose two different Möbius transformation, you get back a Möbius transformation. It's like multiplying 2 by 2 matrices, basically. So question, of course, is that you can ask is, as we iterate these transformations, what is going to be the convergent? Is there going to be a fixed point in the dynamics? Well, okay, this is something I will address right after, but a very small aside that I would like to make is that we can also think of perhaps one of the simplest periodically driven systems, which is the parametric oscillator. So it's really just a harmonic oscillator with a periodic in time-dependent frequency. And depending on the frequency at which you drive the oscillator and the amplitude at which you drive the oscillator, this may develop instabilities. It's a bit like the swing in classical mechanics. There are parametric instabilities. And it's interesting to note that this Hamiltonian H of t actually forms an SL2R algebra in the same way that our deformed CFT forms an SL2R algebra. So the underlying algebra of the Hamiltonian is exactly the same. So one perhaps may expect similar physics, and we may expect some sort of parametric instability to arise also in our driven problem. So in order to understand whether parametric instabilities can arise, we need to understand how Möbius transformation work. So we know that our one-cycle evolution just amounts to a Möbius transformation that you can represent as a 2 by 2 matrix like this, M, A, B, C, D. And then the nth cycle is just like applying this Möbius transformation n times with itself, which is a bit like taking the matrix to the power n, right? So the dynamics of this problem is super simple. And actually, you can just look at the trace square of that one-cycle transformation. And if that thing is smaller than 4, if the trace square is smaller than 4, then there's no fixed point in the dynamics. Meaning that as let's say you're on the unit disk, you're on the unit circle, sorry, and you iterate this Möbius transformation n times, basically you just rotate around on the circle, but you'll never converge to a fixed point. And that can only be, basically be determined by computing the trace square of the one-cycle transformation. Equivalently, the Lyapunov exponent that you can associate to this dynamical system is 0. On the other hand, when the trace square is larger than 4, there is a pair of stable and unstable fixed points that emerge in the dynamics. So it means that all the points on the unit circle, as you iterate that Möbius transformation, they will all flow to the stable fixed point. And in that case, it can easily be shown that the Lyapunov exponent is positive. And sort of the transition between those two cases is when the transformation is parabolic. And in that case, the stable and unstable fixed point, they merge into a single critical point. And yeah, that basically marks the transition between having fixed points and not having any. So, by changing the driving parameters of our drive, by changing our T0 and our T1, we may be able to trigger a transition between different class of Möbius transformations. And we can ask whether going between, let's say, this elliptic and this hyperbolic transformation, that should change something in the physics, in the dynamics of our problem. So this is something we can easily figure out. So yeah, we can write
I ask
our
a question? Sorry, I'm stopping. You have a very nice flow.
No
I
problem.
apologize for stopping it.
Maybe I can go on the previous slide. Yes.
Yeah, just a bit general, just to make sure that I asked you also in the past. But so the conformal field theories are integrable theories. So you expect not to have thermalization or Lyapunov exponent.
Not all of them, actually. If you look at rational CFTs or minimal models, they are completely integrable. In fact, they are, free theories. But if you go to very large central charge, actually, and I will go back later to that in the remaining of the talk, these are actually, strongly correlated CFTs. They have a holographic dual, so that contains a black hole. So yeah, the ones that we realize usually on lattices, yes, they are free theories essentially.
And that's the case where you get the Lyapunov exponent 0 here correspond to such cases, such models, or
So
the parabolic,
no,
for example, or the elliptic.
Yeah, so everything that I'm describing here with this, like this encoding Möbius transformation for the time evolution and all that, this is completely general. It applies to any CFT. It applies to free theories, but it also applies to holographic theories, whatever you want. It's only based on the fact that your theory has an underlying conformal invariance, nothing more than that, and you always have it. So this Lyapunov exponent, for now, you may not think about it as the Lyapunov exponent from quantum chaos. Here's just the naive Lyapunov exponent of a dynamical system, purely classical. It's something different for now. Yeah. Okay. So yeah, so now we have these very different behaviors in our Möbius transformation that we iterate that encodes our time evolution, our stroboscopic time evolution, right? N cycle just amounts to composing a Möbius map n times with itself. So now, as I mentioned before, the stroboscopic evolution of all of your fields just amounts to the change of coordinates z tilde n, where z tilde n is really the nth iteration of the one cycle Möbius transformation that depends on your driving parameters. So now, as you change your driving parameters, let's say T0 and T1, remember we do a two-step drive. T0 is the pulse of H0 and T1 is the length of the time duration of the pulse of H1. Then we need, if we divide those by the system size L, essentially we'll find that sort of phase diagram. So part of the system I'll call heating and part of the system I'll call non-heating. And the way you can determine this phase diagram is actually purely analytically. It is given by the phase boundary between these two phases happens at this transition that I was mentioning before when the transformation, the Möbius transformation becomes parabolic. So essentially, not having fixed point in the dynamics means not heating, and having a fixed point in the dynamics means heating. And yeah, you may ask, why is that so? What do I mean by heating and not heating even? Well, as I mentioned before, we can find explicitly the time evolution of fields. So from the time evolution of fields, we can compute time evolution of correlation functions. And from time evolution of correlation functions, you can, for instance, find the time evolution of energy, E of t, which I define to really just be the expectation value of the homogeneous Hamiltonian in the time evolved initial state. So E of t will oscillate in the non-heating phase, but it will grow exponentially fast with a heating rate given by the Lyapunov exponent in the heating phase. So already that tells you that if you have a fixed point in this Möbius dynamics, that implies that energy will grow exponentially fast. Also, alternatively, one can compute von Neumann entanglement entropy. Again, it's related to correlation functions of peculiar or specific fields. It's called twist fields. In the non-heating phase, it will oscillate with a periodicity that will depend on your driving parameters T0 and T1. But in the heating phase, actually, the entanglement entropy will grow linearly. And again, the coefficient, the slope of the linear growth is given again by this Lyapunov exponent, and also the central charge C appears here. So this is very general. This applies to any CFT, integrable, non-integrable, Ising, free boson, holographic, whatever. And one can find very nice universal relations between the energy growth and the entanglement growth that is given by this expression. So essentially, the growth of energy is the exponential of the growth of half system entanglement entropy up to factors that are completely universal because this is the central charge. So this is the sort of phase diagram that we can find for our Floquet drive, that we can find analytically just because time evolution is encoded in a classical dynamical system in a Möbius transformation. All right, so an algebraic perspective on that result is to compute what's called the Floquet Hamiltonian. So you can write your Floquet unitary. You can always write your Floquet unitary as the exponential of a static Hamiltonian, HF, the Floquet Hamiltonian. And then the whole stroboscopic evolution just amounts to a quantum quench with that Floquet Hamiltonian. In particular, as I mentioned before, both H1 and H0, they form what's called an SL2R algebra. There's only 3 generators in that algebra, which is L0, L1, and L-1. So, of course, the Floquet Hamiltonian has to be in that algebra by, BCH formula. And it will be then a sum of L0, L1, and L-1 with some coefficient alpha, beta, and gamma that will depend on your driving parameters. And so now you can try to understand, what's the spectrum of that Floquet Hamiltonian. And the spectrum of the Floquet Hamiltonian can be deduced by computing what's called the Casimir invariant of SL2. So the Casimir invariant is just given by alpha square minus beta square minus gamma square. So really, once you have this coefficient alpha, beta, and gamma explicitly, you can compute that object. And if that object is positive, then the spectrum of the Floquet Hamiltonian is bounded from below. And that basically leads to the non-heating phase. The dynamics stays very gentle and everything is just oscillating. But if C is negative, the Floquet Hamiltonian is unbounded from below. And this unboundedness of the spectrum, of course, is going to lead to complete blow-up of all physical quantities. So entanglement, energy, and all that, they will grow unboundedly. So in a sense, that's kind of a perspective on this. You just look at the Floquet Hamiltonian. And the same, by the way, happens in the simple parametric oscillator. The same algebraic perspective and conclusion can be drawn for parametric instabilities in the oscillator. All right, so we can ask, okay, as we mentioned, this is all just continuum results. At some point, you'd like to compare it to a lattice because this is perhaps more what we're really interested in at the end of the day. And we can do then a two-step drive between, for instance, a static x-axis chain, so like this, H0, and a spatially deformed x-axis chain, which is given by that Hamiltonian H1, which is characterized by some smooth deformation Vj that depends on the site J. If we choose delta to be between -1 and 1, we know that the uniform x-axis chain, at least, is a CF. I mean, the low energy physics is well described by a Luttinger liquid, which is a CFT. It's gapless. And we can do some MPS calculations, let's say, for a system of 80 sites. We can look at, for instance, time evolution of energy, and we can compare it to our CFT predictions. So in the heating phase, we see this nice exponential growth also on the lattice as we drive the system. But now we see that there's some sort of, there's a discrepancy that starts to appear after, let's say, 15 Floquet cycles, which is to be expected, right? Because you're leaving the low energy sector of the chain. And once you excite higher energy modes, I mean, there's no reason that the system is well described by a CFT. There's really no reason for that. So of course, at some point, the exponential growth would just stop on the lattice, and then the evolution will get more, not analytically tractable, let's say. On the other hand, in the non-heating phase, here we're showing one period of oscillation of the energy. And you can see that for the whole period, the CFT prediction agree pretty well. And that's because here, if you compare the length, the scale of the energy here is 0.01, while in the heating phase is 0.2, is like 20 times smaller. Of course, here you still stay within a low energy regime. And yeah, CFT is a great description. So you could do this numerical calculation for maybe 100 cycles, and the description would still be pretty decent. So yeah,
does it continue increasing if you leave it in time, or eventually will come down, right? Or...
You mean in the heating phase, in this
Yeah.
exponential? Yeah, eventually it will come down. Yeah, exactly. Yeah. Yeah. This is more of a kind of
In
early
a
time.
logarithmic scale, you see it is exponential, right?
Yeah.
Thank you.
Yeah. Yeah. Again, this is a kind of an early
Oh,
time
the CFT. Yeah,
behavior,
yeah.
but yeah, you do see that it's completely exponential. Yeah. All right. So this is for lattice comparison. So now you may think, okay, in this heating phase that's predicted by CFT, well, things must be boring. Because energy grows exponentially, entanglement grows linearly. No way this is interesting. But actually, if you actually look at the spatial distribution of energy in the system, so let's say you look at energy density, so it's really just the time evolved expectation value of the energy density, which is called T00. It's the energy momentum tensor. So again, you can compute that object explicitly because T00 is represented by a sum of chiral and anti-chiral, what's called quasi-primary fields. So again, you can encode the time evolution of these fields by coordinate transformation. Now you have an extra term that contains the central charge. It's basically related to Casimir energy. And you can compute that one-point function, that expectation value analytically. And what you find is that on the continuum here, it's really at the CFT level. If you start, let's say, from the ground state at time 0, so your energy density is just flat, it doesn't depend on space, right? It's translationally invariant. As you drive the system, the energy will grow exponentially only at 2 points. So you see there's these two kind of hotspots where energy grows exponentially fast, but actually it doesn't grow at all for the rest of the system. Actually, if you go to long time, you'll see that the energy actually decays exponentially everywhere else in the system. So if you look at energy density, you see that actually the heating is very spatially structured and spatially inhomogeneous. It just goes in 2 points. Alternatively, you can look at how the entanglement entropy behaves in the system. So you can look at von Neumann entropy for subsystem A, whose length is variable. So here, the length of the subsystem A will be given by what I call X. So then what you'll do is that you'll change X along the chain, along the system, and you'd see how the entanglement will change, how the scaling of entanglement will change as you do the drive. And the plot that you get is something like this. So let's say you're at time t equals t, the blue curve here. You would expect the usual CFT result if you start from the ground state. The entanglement entropy just goes as log L. So you get this sort of inverse U-shaped curve. Now, if you change the position of X, right, and you look at the time evolution of the entanglement entropy, it seems that once you passed some threshold that is a bit like around 2, let's say, once you pass this threshold, in time, the entanglement entropy will grow linearly. But once you pass the second threshold, then the entanglement entropy does not evolve in time anymore. So essentially, what that means is that the entanglement entropy will grow linearly in time if and only if A contains a single of these hotspots. If A contains one of the two hotspots, essentially the entanglement grows linearly in time, which seems to indicate that all the entanglement entropy in the system that you generate with the drive gets concentrated at the two hotspots. So this is what you conclude by looking at energy density evolution, and entanglement entropy evolution. You see that it seems that this hotspot, concentrate all the energy and all the entanglements. And now you may ask, yeah, how can I understand this from, an intuitive picture, let's say quasi-particle picture? And this is where Kerr spacetime will actually kick in. So we have an inhomogeneous system, which can be seen as a homogeneous critical theory on a curved background. So usually, if you have a homogeneous theory, you have that the quasi-particle, they propagate at some Fermi velocity v, and then that gives basically the slope of the light cone. So you put some excitation, let's say at x0 at time 0, and you look at how the excitation will propagate in the system. And because the quasi-particles are gapless, they will propagate at the speed of light, the Fermi velocity, speed of sound. And the light cone will be straight. But now if you have an inhomogeneous theory that is spatially deformed by this function v of x, it is like giving the quasi-particle a group velocity v of x. So now the group velocity of the quasi-particles will not be constant in space. It will depend on space. So of course, if you look at the kind of light cone of the excitations, they will be a bit, this light cone will be wiggly, right? This is expected. And the way you can even find this light cone is by finding the geodesics of that curved space-time. ds squared is equal to dx squared minus v squared of x dt squared. So you give me a deformation v of x that gives, the velocities of the particles, the quasi-particles, and I give you a curved space-time, and I tell you that the gapless quasi-particles follow the geodesics of that space-time. And this actually has been observed, this curved light cone in gapless systems has been observed recently in some quantum field simulator that was made by using two tunneling coupled superfluids in that PNAS paper. So here they were basically simulating a Luttinger liquid that had a spatially dependent Fermi velocity. So yeah, these things have been observed. So now you may think, okay, I have a critical theory where I have these gapless quasi-particles that propagate with a function v of x that depends on space, but also depends on time. So it is, in principle, a very complicated problem, but you can always just look at the Floquet Hamiltonian, and then, the time dependence is kind of gone. Now you have a static Hamiltonian. So the Floquet Hamiltonian is, again, inhomogeneous. The deformation is given by this Vf of x, where f denotes Floquet. And the explicit form in the heating phase of that Floquet, of that deformation Vf of x is this thing. So for those who know, this sort of Hamiltonian is called the entanglement Hamiltonian in a CFT, or it's also called modular Hamiltonian. What's important is that this V of x goes to 0 when x is equal to x star and x is equal to L minus x star. So x star is really the position of this emergent hotspot. And okay, what you can do now is that given this Vf of x, you can associate a curved spacetime, right? A metric. And you can now expand that metric around, let's say, one of the two hotspots. Let's expand it around x star. Well, if I expand my metric around x star, I get this. And this is exactly the curved spacetime that is generated by a horizon in 1+1 dimensions. So this is the sense in which we can say that we have this sort of black hole-like excitations that are arising. And intuitively, it's very simple. What happens is that the quasi-particles, the velocity of the quasi-particles goes to 0 at this point. So because it goes to 0 at this point, it would take an infinite time for the quasi-particles to reach the point. And well, that just leads to horizon physics. So in particular, you can associate a Hawking temperature to that horizon. And funny enough, this Hawking temperature gives you the heating rate. It gives you the rate at which energy increases in your system. And you can go a bit further. You can look at how quasi-particle really propagates in the system by computing two-point functions at different times. So what's called dynamical two-point function. If you put an excitation, for instance, in this point here, about 30, and you look at how it propagates in the system at stroboscopic times, you'd find that essentially all the chiral quasi-particle go to this point here, and all the antichiral go to the other point. And this you can also see by looking at, let's say, SZ correlation functions on the lattice. All right, so yeah, and the red dashed lines are just geodesics of this curved spacetime, so it matches very well. Okay, I would just briefly like to mention something that I find quite cute, is that all the quasi-particles, they go to one of these two hotspots, and all the entanglement is carried by these quasi-particles. It means that if you start from a if you start from a thermal state at time 0, and now you start to drive the system with this Floquet drive, what would happen is that all the excitation of the thermal state, they would aggregate in the horizons, and what is left in between would basically be the vacuum. So if you look at the entanglement entropy of a subsystem A that is in between those two emergent horizons, then the entanglement entropy at time 0 is, following volume law, so it scales linearly with subsystem size. But as you evolve the system, because all the quasi-particles get, they leave that part of the system, basically you're cooling down to the ground state. So now you have the kind of logarithmic violated area law usual from the ground state of a CFT. And this can, in that paper, people computed the evolution of entanglement entropy. So at time 0, you're in a thermal state. You do the Floquet drive, and as you do multiple drives, you basically cool down to the ground state entanglement entropy. And this matches pretty well also with lattice calculations. So in a sense, this system acts as a sort of entanglement pump where all the excitation, all the entanglement, and all the energy gets concentrated at spatial locations, and all the rest just cools down to the ground state.
Don't you get back reactions from the horizons?
What do you mean by back
Like
reaction?
if you have two particles, do they go through the horizon immediately, or?
It would take an infinite time for them to reach
Okay.
the horizon because basically the velocity, the group velocity goes to zero exactly at the horizon. So, it takes an infinite time for the quasi-particle to actually reach that point because as they get closer, their velocity, gets
Okay,
closer to zero.
that's why you take A to be a small region within your black hole. So
Here, no,
the particles now they get frozen near the horizon, but they leave your A region.
So if I take my A region such that it does not contain any of those black holes, that's the point, because all the quasi-particle, they will leave the regions where there's no black holes. If I were to take
Sorry,
yeah,
A could be inside your black hole. I mean, you
sure.
have two horizons, right?
Yeah. So then if you were to take A, like around one of the two horizons, entanglement will grow linearly in time. It would just increase and increase and increase because all the entanglement is shared between the two
You
black
mean
holes.
the boundary of A at the horizon, then it will increase.
I mean that the subsystem A contains the point where there is the horizon. The horizon is a single point, and if A contains that single point, then entanglement will grow linearly in time. And if it does not, then it will actually decay back to the ground state.
Okay, yeah.
That's what I'm saying. Yeah.
Good, thank you. Yeah.
So okay. Now maybe for the sake of time, I'll go a bit fast here, but there's a fun classical analogy that one can make, which is basically light in a modulated cavity. So just imagine light in one dimension, in a cavity with two mirrors, and now you move one of the two mirrors periodically in time. So this is what is illustrated on that figure. What's fun is that the different light rays, depending on the frequency at which you're moving the mirror, all the light rays may accumulate on a single characteristic, on a single trajectory, if you wish. And if you look at this stroboscopically, it basically leads to exactly the same physics as what I just described. It's a gapless theory in a modulated medium. And in particular, if you look at energy density, so that was done in this paper from Ivar Martin, if you look at evolution of the energy density at stroboscopic times, it will grow exponentially fast because here x-axis is really logarithmic. It will grow exponentially fast at one point and it will decay everywhere else, which is exactly what we're observing in our critical theory. And also, if you look at in evolution here, the rightmost plot is evolution of total energy as a function of time. It grows exponentially in time. So it is sort of the same thing as the heating phase that I just described in our system. But here in some sense, you could imagine the fact that we're moving, the fact that we're changing in space the velocity of the quasi-particles. It's a bit like if I was putting light in some medium where the refractive index depends on space, right? It is, you can really draw a very close analogy to this kind of more optical setups. And actually, in that paper, they also describe similar stroboscopic horizon physics interpretation, interestingly. All right, so now I'd like to go to quantum chaos. So so the motivation now to study the scrambling properties of these horizons, well, comes from what I was discussing in the introduction, that it's known that black hole horizons are the fastest scramblers. So as I mentioned in the intro, the SYK model, the SYK model is like the SYK model is saturating the bond on quantum chaos. There are different quantities that you can compute to characterize the scrambling in the SYK model, for instance, OTOCs, or also spectral form factor, which is some sort of generalized partition function, which has in chaotic system this typical deep RAM plateau structure that actually comes from random matrices. Because if you take some random Gaussian unitary matrices, they will basically have the same shape for the spectral form factor, where this RAM plateau structure kind of comes from level repulsion of the states. So this is another kind of very famous diagnosis of quantum scrambling on top of OTOCs, which is these are perhaps the two very popular proxies for quantum chaos. So anyways, now we're going to focus on OTOCs anyways. So now I'm coming back to the question that Yanis asked before about whether CFTs are integrable or not. Rational CFTs, minimum models, and all this, they are integrable. They are known to be integrable. So you don't expect any chaos, even if you drive it. If you drive it the way I'm proposing, which basically retains conformal invariance, there's not going to be any chaos that's going to appear because you're still preserving the integrability of the underlying CFT. On the other hand, you can look at large central charge CFTs, and these are actually strongly coupled, strongly correlated, and are chaotic. And this has been shown explicitly. People have computed a decade ago the OTOC in a CFT in a thermal ensemble at large central charge. Essentially, it boils down to computing a 4-point correlation function. So here it gets a bit technical, so I'll go kind of fast. But all I want to say is that when you want to compute a 4-point function in CFT, the 4-point function is not completely fixed by conformal invariance. You need a bit more. You have this function f of z bar, where z is what is called the cross ratio between the 4 different coordinates in your 4-point function. And this function f is theory dependent. It will be a different function f for different conformal field theories. What's important is that in holographic theories, in the limit of large central charge, this function f has some monodromy properties such that if the cross ratio crosses the real positive axis as a function of time, then this 4-point function has a very non-trivial evolution once you impose the OTOC ordering of the operators. The final result is this. It was opened by Roberts and Stanford. It basically tells you that the OTOC, this 4-point function, decays exponentially fast as a function of time. And the Lyapunov exponent that characterizes this exponential decay is given by 2 pi times the temperature, which is the bound on quantum chaos. Thus, CFTs at large central charge, which are holographic to a BTZ black hole, they are chaotic because they have a holographic dual that contains a black hole. That's a very kind of classical result for more in the high energy physics literature, let's say. Now we can try to do the same because, as I mentioned before, our system, our Floquet drive, it works for any conformal field theory. So it also works in the holographic limit of large central charge. So you can, let's say, start from the ground state of your theory and now drive it. So instead of starting from a thermal state at temperature beta inverse, we start from the ground state of the theory, but now we drive it in the heating phase. So the driving is equivalent to do a quench with our Floquet Hamiltonian. That's exactly the Hamiltonian I described before. You can do the whole 4-point calculation using the same kind of tricks as was discussed in the literature for CFTs at equilibrium. But now you can use the fact, as I mentioned before, that your time evolution amounts to a coordinate transformation and can, by coordinate transformations, be mapped to equilibrium correlation functions. So using all these small tricks, well, you can compute the OTOC, find that it decays exponentially fast. And the very nice conclusion is that, you started from a system that's not in a thermal state. There's no physical temperature. But you have these emergent horizons that appear in the system that are characterized by Hawking temperature. So what is really, I think, nice or beautiful is that the Lyapunov exponent that characterizes exponential decay at early times of the OTOC, the OTOC, is given by 2 pi times the Hawking temperature of the emergent horizons. So from that perspective, although the system is prepared in the ground state, the dynamics appears to be thermal in this sort of drive. Also, remember that our system is strongly inhomogeneous. So maybe the scrambling may be as well inhomogeneous. So it turns out to be the case, and in particular, the butterfly velocity depends on space and is given by the Floquet velocity. So it's given by the deformation that characterizes our Floquet Hamiltonian. And one funny consequence of this is that, remember, we're doing a 2-step drive. We're alternating between 2 static Hamiltonians for time t1 and t0. But as you change the value of t1 or as you change the value of t0, the position of those horizons is going to move around. The position of the horizon depends on your driving parameters. So then, if you put, let's say, your 2 operators v and w at different sides of the horizon, there's no scrambling of information, basically. The OTOC does not decay exponentially. There's no chaos. Now, as you change the driving parameters, the position of the horizon is going to move. and eventually it will go past V and W. And in that case, if they're on the same side of the horizon, the OTOC will decay exponentially. So in some sense, you can have transition from chaotic or scrambling to non-scrambling regimes simply by tuning your driving parameters. So you can really Floquet engineer chaos to non-chaos transitions. So all this is very, okay, all this works in the limit, in the holographic limit where the CFTs are chaotic. But I would also like to mention that integrable CFTs, although they will not display any chaos, any exponential decay of the OTOC, they will still display very interesting properties at late time. For instance, you can extract what's called the modular S matrix of the Ising CFT, for instance. So you can extract some topological data, I think, by looking at late time values of the OTOC. So it's still quite interesting to try to simulate this OTOC, let's say in Rydberg atoms or in some quantum simulator. So that's something I'll briefly mention now, that it will be interesting to kind of, simulate this OTOC in quantum simulating platforms. But as I mentioned in the intro, it's very hard to implement this backward time evolution that is characteristic of the OTOC in real experiments. So it turns out that in our problem, it is actually pretty simple to change the sign of the Floquet Hamiltonian. Changing the sign of the physical Hamiltonian can be a pain in experiments, but we can actually find a very simple way to change the sign of the Floquet Hamiltonian. And that will lead to backward time evolution, at least at stroboscopic times. So the idea is the following. So let's say you're in the heating phase, so you take your parameters T0 and T1 to be here. You take those values, let's say, and you do this two-step drive. And then you create these emergent horizons and all that. Now you'd like to go backward in time in order to simulate the OTOC. What you can just do is that you can keep exactly the same Hamiltonian H0 and H1. You don't have the need to try to revert the sign of the Hamiltonians or anything. You just need to change the duration of the pulses. So instead of having these T0 and T1 that are given here in the phase diagram, you kind of take the symmetric with respect to the center of that phase diagram. And if you take this value here, then you have these new parameters T0 tilde and T1 tilde, and effectively at stroboscopic times, this will bring you back to the initial state. So that is a representation of the inverse of the stroboscopic evolution. This is, of course, working perfectly on CFT, but you may ask whether it works well on the lattice. So we did some lattice calculation of the fidelity of this backward time evolution procedure. So you start from some initial state psi 0, you do n cycle into the heating phase. Then you do n over cycle with the new duration T0 tilde and T1 tilde, and you hope to be more or less back to the initial state. So that thing should be 1 if it was perfect. We do it for different system sizes. So these are the different curves. And we do it for different values of n. So the longer n is, and of course, the longer you're driving the system into the heating phase, and at some point, it just so happens that the CFT description is not good anymore, and you cannot really revert back to your initial state. But you can see that for, let's say, 100 Floquet cycles, let's say, by increasing system size, you have a dramatic increase or dramatic improvement of your fidelity. And here, I think it's a free fermion lattice, so we can go to fairly large system sizes. I think it goes from 100 to 1,000 sites. And you see that as you go to the blue curve, basically, you still can recover completely your initial state, even after 100 cycles.
Is it improves with system size because you go closer to the CFT prediction?
Yeah.
In the
Exactly.
All right, thank
exactly.
you. Yeah, because it's pretty cool, actually.
It actually works because, I mean, yeah, this thing works perfectly on the CFT. Of course, on the lattice, there's a breakdown, but as you increase system size, it gets better. Of course, at some point, even if you go to 1 billion sites, you will still not be able to recover the CFT if you drive very, very long. But if you do not too many cycles, let's say 100 is still quite a lot, I think, you can still pretty much recover your initial state. And here you have an illustration of the energy density evolution in the system. So you start from the ground state. You kind of excite these black holes as you drive the system. And now you change the driving parameters, and the system is going backward in time, and this horizon evaporates, so to say. And you're back with almost the initial state, but you can definitely see that there are ripples in the final state, which is the signature that, of course, the final state is not exactly the same as the initial state. Okay, so that brings me to my conclusion. So you've been studying a class of solvable critical-driven models. They have nice kind of inhomogeneous heating features with this horizon that appear in space. And interestingly, in the limit of large central charge, these horizons are really scramblers of quantum information. And in particular, you can write some sort of Floquet counterpart of the on the bond on quantum chaos, where the Lyapunov exponent now is given by the Hawking temperature of these analog horizons. Okay, and there's lots of interesting questions that could be explored further. So for instance, going to higher dimensions, this should still be doable from CFT perspective. You have a bit, the toolbox is a bit smaller, but you can still do quite a bit of stuff. And also, what about non-unitary evolution? And also, along this line, I'm very interested to apply some weak measurement around this one of these two horizons. You can create more than two horizons, by the way, and they always share entanglement. But I'm very interested to do like some measurement around one of those two horizons. This should, of course, this should decrease the entanglement. And if you do this with a certain probability by alternating between unitary evolution and measurement, maybe you'll be able to see some nice kind of measurement-induced space transition-like features. Okay, so that's the end of the talk, and thanks for your attention.
Thank you. Very nice.